Okay, guys. So you guys hear me? Give me a signal when you can hear me, okay? Perfect. We have a lot of old friends, so using the Zoom is not a big problem whatsoever. You know what? Let's give it one more minute, maybe 2 more minutes, while we're receiving more attendance. This is our first lecture. Always people are having some experience, having some issues, right, based on the first lecture. Let's give it maybe 2 more minutes while we're receiving more attendance, okay? Always there are some situations happening from time to time. 2 more minutes. Come on, what are we doing today? We're doing the number theory, okay? Yeah, that's number theory. Or maybe give you guys some introduction how to stay healthy in the coronavirus. Stay away from all the crowd. All right, let's give it 1 more minute while we're receiving attendance. There are still some problems. Some students have some issues logging into our Zoom. Okay, so that's the reason I always asking you guys to be, especially for the first lecture, to be here maybe 15 minutes earlier if there's any issues, so on and so forth. Yeah, for the haircut, you know what? Actually, my friend helped me do the haircut. And I told you guys in our Euclid lecture, I didn't have a haircut for a long time. My hair is that much long. So anyway, I have to use the haircut. She gave me a haircut. So it's not nasty, right? All right. Okay. More students have more problems. So what, you're going to be home for 2 weeks. Yeah, my company is actually working from home for 2 weeks. That's pretty much the situation. We'll see. But for now, it's only like 2 weeks is only like a current solution, right? We might go for more than 2 weeks. All right, so let's get started. I think it's 12:32. Let's get started. So you guys can see my screen, right? Let me know if you guys can see my screen. All right, so welcome guys, welcome and bienvenue, right? Welcome to our lecture. A quick, before the lecture gets started, I'd like to give you guys a little bit information, talking about who we are, where we come from, what is our target, so on and so forth. We have some old students coming from our previous lectures, our Euclid lectures, so on and so forth, and we still have some new students. So as a common practice at the very beginning of the lecture, especially lecture number 1, I'd like to give you guys a little bit like a rational understanding, like introduction about our lectures, and give you guys a whole picture what we're talking about for the next few lectures. So the first one, what we're talking about is the background. So the lecture is actually created as a contingent plan, right? We have like 2 weeks, maybe more than 2 weeks in the long run for our, no classes. So in the special time, I talk with different parents, and parents talk to me that maybe we can take advantage of this time to give us some boot camp. So students are back at home, they wanted to, have more focus into our mathematics topics, so on and so forth. So this will be considered as a special time trial, special time treat for students who would like to, get deeper for the mathematics. Well, the second part is why we want to choose the topic for the number theory. I actually have some discussion with different parents, and we like to pick up a topic which is kind of like independent, because students might come from different backgrounds. You might have a very good understanding from mathematics, or maybe not. So we want to pick up a topic which is kind of segregated from most of the other topics. If I choose the algebra, there's a big bind between different topics, right? Well, if I choose a geometry, maybe it's a good option, or maybe you can choose number theory. Like the rationale behind that is because number theory is actually an extremely important topic, especially for the math competition. Regardless, you go to AMC, you go to the Canadian exam, all the way you go to AME, CMO, IMO, they always put a lot of emphasis for the number theory, because number theory is very comprehensive part. It can have a lot of connections with different topics in our entire math domain. Well, the other part is that because number theory, you can barely learn that in your day school, right? In your day school, you basically give us some divisibility, some prime numbers, composite numbers, but that's pretty much for it. They won't go really deep into the rationale behind different important theories for the number theory. And that's actually kind of like a gap between our regular lecture and our mathematics competition. And to bridge the gap, students can go to different lectures, AOPS, or different like schools. So that's kind of the reason we like to, take this opportunity to give us a little bit overviewing and a little bit in-depth overviewing to show us all the important topics for the number theory. All right, so that's our background. The second part is the language. So I gotta say, a long time ago, about like 2, 3 years ago, almost all my lectures are actually bilingual. So whenever I say bilingual, it's actually French and English. And because by the time then there are a lot of students coming from Quebec, so they like to have the bilingual lectures back and forth. But these days, since I'm actually more focused my education in Ontario or some other provinces rather than Quebec, so my lecture becoming more and more unilingual. And also my French get deteriorates. If you didn't practice a lot, your French is getting worse and worse. So for today's lecture, let me ask you guys, does anyone speak French? Quelqu'un qui parle français ici? You can give me some feedback from your group chat. You want to speak some French? I know Leo comes from Quebec. Leo parle très bien français, c'est bien sûr. Mais what about the other guy? Like the d'autres gens, quelqu'un qui parle français? A little bit? Because you know what? French is very important. Crois-moi, le français est très important. En particulier, pour toutes les collaborations avec les gouvernements du Canada, le gouvernement du Québec, le français est nécessaire. So from time to time, I do some lectures with the government. There's some, free broadcast, like a podcast and so forth. If you want to work with the Quebec government or the federal government, French is very important. Especially you guys. I think you guys are going to go to French immersion or those kind of things. So I think French is actually a very good add-on for your normal languages. And also, there are two real advantages for French. The first one is if you guys want to go to, I don't know, if you guys want to go to COMC, or if you guys want to go to Euclid, in that case, French is, you can actually solve the problem using English or using French, right? So you know that, right? My experience says that if you use French, you know what? Most of the English teachers, they have no idea what they're talking about, right? So they're going to forward your exam into the French teachers. And if you can write an exam in French, the French teachers will be more, comme on dit en français, gentil, nice. They will be more generous to you. So even you have the same quality of the paper, if you write in French, French teachers tend to give you higher marks. This is the stats. I'm not saying this in the middle of nowhere, but this is kind of the stats. And second part is that, even though you're in Ontario, if you can, use some services, these days, if you want to make a phone call to the Service Canada, you won't be able to get connected, right? Because everyone is actually doing that. But c'est parler français, c'est plus vite. If you want to talk in French, you choose choose your language from French. You don't have to wait for 3 hours before you get connected. You can get connected immediately. So that's kind of like the reasoning I want you guys to learn some French, at least some functional French, right? Sometimes French can give you a little bit shortcut. If you want to go for the CMO, you go for the regular COMC, it's very challenging. But if you go for the Quebec routine, it actually can give you a little bit shortcut. So, but these days, I assume that most of this, je suis fatigué, is only in French. Okay, so, but pretty much these days, I think most of the students, they don't even speak to a word of French. So most of my language is going to be in English. All right. Moving forward is the new format. Right. So these days, for the students who have been with me for a long time, he or she will be knowing that normally my lectures goes for two categories. The first category is like a live lecture, like we're currently working on, right? You can ask for questions, you're gonna have the real-time feedbacks, everything happens in a real-time basis. That's pretty much like the regular live lectures. Well, I also have the pre-recorded lectures. You guys can do the purchase from my website. The pre-recorded lectures is kind of like cheaper, and you pretty much have the same content. It's actually a record of the existing lecture, but you won't have like a lot of interactions. If you have any problems, you can reach out at me, and through WeChat or like Facebook Messenger, so on and so forth, right? That's like the two categories. Well, for this time, I'm actually advertising a new, like kind of like a new collaboration pattern, which is a delayed live lecture. So what is a delayed live lecture? It's kind of like a combination between the two. So you have the live part, like the part I'm currently working on. I'm talking to you guys, you talk to me, so on and so forth. While the live part is more like for the introduction, I want to give you some basic background, so on and so forth. But as long as we go to the real content, I'm going to give you as what is called like the pre-recorded lectures. So the pre-recorded lectures is the lecture I did before. I record the lectures so you guys can see the lectures. So this is kind of like a pre-recorded part. However, I still going to be here, give you guys the real-time feedback for all your questions. While you are basically watching the pre-recorded lectures, if you have any questions, you can type it in the group chat. I suggest you type it in the group chat. And as long as I said it, I'm going to be give you the feedback, the real-time feedback, something like that. And the rationale behind this, why we like to do is kind of like a pre-recorded plus the live, is because that this is how the university works. I'll give you some experience, my real experience when I went to McGill University. Previously in our high school territory, if you have any questions, because we have a relatively small size class, right? Have any questions, you talk to the teacher right away, and the teacher will give you the information right away. So this kind of communication is very dynamic. However, as long as go to university, like normally speaking, a lecture will contain maybe 100 or 200 students. It is impossible for the students to ask a question on the fly, and also impossible for the teacher to answer everyone's question on the fly. So this is how it works. Normally, the teacher will go for a topic, and this topic may, I don't know, maybe go for maybe like 10 minutes, for instance. And then after 10 minutes, the teacher is going to stop. Ask you guys, okay, you have any questions regarding what I just teach you in the last 10 minutes? Stuff like that. So somehow you need to find out, you need to learn such a new study pattern that as long as you have a question, don't raise it right away, write it down, keep your mind, while after 10 minutes, as long as there's a gap, so the people can answer the question. So the teacher will answer a question. So this is how the university works. And the second reason behind is that, my experience when I was in McGill, there was a lecture called Advanced Computing. So the lecture per se, like the textbook contains almost like 2,000 pages, and we only have like 10 lectures. So that being said means the teacher has to go over almost like 200 pages per lecture. The lecture is only 2 hours. So that being said, the teacher, whenever the teacher says something, is actually in the blasting fashion. All the information goes like this, right? It is quite possible that sometimes you get stuck at a certain point. Well, instead of really get tangled for that specific point, a college or like a university student need to do is that try to buy it ASAP. Let's say the teacher that blah, blah, blah. Okay, now A plus B equals to 2. Maybe you have no idea why A plus B equals to 2, but as a college student, you need to say, okay, let's buy it. A plus B equals to 2. And then moving forward, you will follow the thought of the teacher. Then after maybe 10 minutes, when the teacher have a breakdown, he will talk to you later. Okay, so any questions? You want to ask me why A plus 2 equals to 2. So by the time then, you'll be able to project your question. So that's kind of like the rationale behind this. So in the university level, you need to, as long as in the middle of the lecture, you got tangled, you got something wrong, buy it. Take it ASAP and graduate, and then moving forward to the next topic. So this is actually a training process. So that's actually the reasoning why a lot of students, when they jump from the high school to the university, they find a big gap because the way how teacher organize the lecture can be changed significantly. So this is considered to be a high-level lecture. So I assume you guys have more understanding for the concepts and also higher grades. So let's do it gradually by gradually. Okay, I'm trying to give you more trainings in this process. At the very beginning, I might, I don't know, touch base with you every 10 minutes and 5 minutes, but gradually by gradually, I'll touch base with you for every one problem. I'm going to give you the explanations after one problem. All right. So moving forward, interactions. Interaction is always more than important. Regardless, we're doing a face-to-face lecture or we're doing an online lecture, it's always important. It's actually more than important that you guys can tell me what you think. If you get stuck, if you have any questions, please let me know. If you find it a little bit uncomfortable talking in front of the public, you can use the private chat feature, right? I don't know if you guys are all familiar with Zoom. You should be. On the top left corner, you're going to see there's like the console, operation console. You see mute, stop video. All the way, you see the annotation and then more, the three dots saying more. You click the more option, you're going to see a chat, right? The drop down menu is going to say chat. So you will be able to see all the chats in this classroom. If you want to talk to a specific person, if you want to talk to me, you can always use a private chat. So I'm always monitoring the chat section, try to make sure any questions can be picked up and can be answered on a real-time basis. All right. Moving forward, homework. Homework, I believe, is actually a very important part. This is actually an extension of our lecture. So, excuse me. So every lecture, we're going to have a assignment. I'm going to publish into our Google class. For the Hawk class, we have four problems for each lecture. So normally speaking, you should have almost like a week to finish all the four problems, right? That's our regular pattern. However, for this special case, you only have like one day. So it's not a big deal whatsoever. Try your best. If you have time, try to do the work, upload it into the Google class. I will mark it for you. I'll give you the feedback, which one is correct, which one is incorrect, what is the hint, so on and so forth. If you do have some problems, no problem. You don't really have time because I know some private schools are still open these days. So no worries. Every lecture, we're going to give you the homework. For the beginning of the next lecture, we're going to go over for all those problems one by one. Okay, we want to make sure that every single problem that reads up during our lecture, you can 100% understand. Because all those problems are carefully picked up such that we can make sure all the topics, all the important concepts that we talk about during the lecture can be further reinforced by using our assignment. Okay? And if you do the assignment, you can let me know. You can basically, upload it into group chat. From time to time, normally I will ask the students to give us a presentation to walk us through for all your problems, all your solutions. Because these days, why I keep doing this, I believe think aloud is actually very important. In the future, if you guys want to go to Google, or because you want to go to Facebook, for instance, you want to go for the code interview, right? Because I'm doing computer for all my life. So the code interview is not actually giving a laptop. You go there, basically give me the code. No. On the contrary, they're going to give you a whiteboard. You can actually write your code on the whiteboard and then walk us through for the entire process. So it's not 100% accurate for if you have a syntax error, so on and so forth. It's not significantly important because the idea is going to help you fix the problem, right? Eventually, how do you think aloud? Guide us through the process. This is extremely important. For a high-level lecture, I think you guys need to really put a lot of emphasis in this process. Again, you guys can be 100% sure as long as I ask you guys to do a presentation means that you did a fantastic job in this assignment. So I won't make you like a fool, right? You actually did it wrong and then I let you do the presentation in front of the crowd. This is not going to happen. So try to be 100% calm down. Yeah, so that's pretty much for the homework part. And then moving forward, we're going to go to the presentation part. Normally speaking, for every lecture, we're going to ask one student to do a presentation. So the presentation, you don't have to find out a super complicated problem, not necessarily. It can be a relatively straightforward problem. You can walk us through. You can act as a teacher. The most important thing is that like the time, there was a saying that if you want to learn something fantastic, you just be a teacher of it, right? As long as you're a teacher, you're trying to explain the situation, explain the concepts to the other students, then you need to really dig it deep. You need to have like what is called like an in-depth dip into the concept. And I find out this part actually gives a lot of the top tier student a very good opportunity to show the way how do you speak and how do you guide the others. I know, if you have some very top students, sometimes you can also find a summer job or something at certain education, like an institution or something. They can ask you to be a teacher, teach other students. So this is quite common. So I want you guys to take this opportunity to show the way how to do the presentation. If you only know this is far more than enough, far away from enough. Most important thing is you need to present it in a very, what is called, in a very regular fashion, in a very professional way. So in the future, I think this is going to be very helpful for you guys. Again, this is not compulsory because normally you have like a week to do the presentation, to do the preparation. But these days we're kind of tight. It's only everyday lecture. It's up to you guys. I'm going to be asking you guys if there's a volunteer they want to do the presentation, let me know. Otherwise, I'm just going to move forward with our lectures. All right, I think that's pretty much a short and brief introduction to our lecture. At the very beginning, there's a little bit cliche for the old students, but I think for the new student, hopefully give you guys a little bit heads up where we come from. All right, any questions to me? Any questions for me? All good? All right, if go good, let's get started. Let's go to the recording part, okay? And like I said, I'll be here, so I won't be going anywhere else. I'll let you know how it works. Okay, just give me 1 sec. I'm gonna do this. Let me know if you kind of see the screen and can see all the content from there. Now, let me write something from here. Okay, we're gonna focus on the number theory in the last few lectures. Can you guys hear me? You know, number theory is actually very important and also a very difficult part in the math competition. I'll be here. Right? If you go to Euclid, if you go to COMC or AMC, they're gonna, especially the last few questions, they're gonna focus on the number theory a lot. So number theory is an important part. We're gonna spend a decent amount of time talking about number theory. Actually, number theory is actually a very old topic. Whenever people realize there are numbers, they start talking about the number theories. Number theory is nothing but trying to find out the patterns or the principles for all those numbers. We'll talk about the principle, about the prime numbers, composite numbers, modular, arithmetic. There's nothing more but trying to understand the basic principles of different numbers. You know, Gauss, a very famous mathematician, used to say that mathematics is the queen of science, and number theory is the queen of mathematics. Just trying to say how important number theory is. And after Gauss, actually, people modify Gauss's word a little bit. They say mathematics is the queen of science, and number theory is the crown of the queen. And the Chinese people actually add another one afterwards, saying the Goldbach Conjecture is actually the pearl on the crown of the queen. So one, you can see like different levels, more and more important one after another. So before we go to like the number theories, we might see a bunch of names. These are the very glory, very shining names in the history of number theory. I'd like to give you those names, and you're gonna keep seeing these names for the entire course of our number theory. The first one is Euclid. You know, our Waterloo exam is actually named after this famous mathematician, Euclid. So most of you guys should know Euclid is a very famous mathematician for the geometry, right? He is a geometrician. But actually, he also did a lot of contributions for the number theory. For instance, he has proved there are infinitely many prime numbers. You know, there are many prime numbers. People might think this very intuitive. There might be infinitely many prime numbers. But in mathematics, we always need a accurate, a rigorous proof. So Euclid is the first person who gave a rigorous proof that there are infinitely many prime numbers. And in our lecture, we're also going to give you us this proof. There are millions of proof how to prove there are like the infinitely many prime numbers, but Euclid's proof is the most it's the most brief one. So we like to introduce you guys the proof that given by Euclid, and trying to use the same methodology, we can prove some other problems. And Euclid is actually 300 before the century. And he also found out the fundamental theory of algebra. You guys know the fundamental theory of algebra? There are different formats, different ways of presentation. But one of the most important presentation is that for any positive integers, the prime factorization should be unique. If you have an integer, a positive integer, you like to do a prime factorization. So this factorization is unique. talking about the prime factors and corresponding exponent of all the prime factors. So this one is unique. So Euclid is a famous guy we gotta know. The second guy is the Fermat, or in English, Fermat. Fermat is actually a very famous 17th century French mathematician. He's very famous about a lot of principles. He's a super smart guy. And his greatest contribution for the mathematician are actually two. The first one is the Fermat's little principle. So this principle is very important. We're going to introduce during our lecture. Well, the second one is the Fermat's last principle. This guy is actually a very famous conjecture for super long time. Actually, Fermat create or present this principle. I mean, by the time there's only a conjecture because there's not a real rigorous solution. And all the way until 1995, a British mathematician, Andrew Wiles, is the first person who proved this conjecture. So this conjecture changed from a conjecture to a principle, to a theorem. By the time then, I just want to say a little bit thing about like Fermat. By the time then the mathematicians actually do communication using, they can't send email, right? By the time they're using like a basic mail. So they basically write a letter, their friend. Fermat keeps saying that, okay, I find a new principle. However, due to the limited space of our letter, I can't really give you the proof, but I have the proof already. So he keep doing that for all his life. So especially for this guy, he claimed he has already found a solution, but due to the limited of space, it doesn't really show up like the solution. However, people never find out a solution until almost like 200 years. So, people really have no idea if Fermat really have the solution, really have the proof or not. So it's more like reasoning the problem. In Chinese, the part we say it's pretty much like 挖坑啊, just like 郭德纲,挖坑专业户. You really like to raise a question, but rather than giving a solution. That's pretty much for Fermat. So this one is very important. We're going to introduce during our lecture. This one is actually a super complicated problem which confused the human beings for almost 300 years. And after, Andrew just basically published his solution, there was an interview by a journalist. So actually the journalist asked for Andrew, do you think Fermat can actually prove the problem 300 years ago while you proved after 300 years? So Andrew's solution is that, his response is that this problem is a 20th century problem. So no one can prove it before the 20th century, so you have no idea. So most likely Fermat doesn't really have the solution for it. Well, the other important name you guys are going to see from time to time is going to be Euler. Euler is pretty much a god or like a time traveler. Let me just give you some brief about his biography, and you can realize how strong, how super he is. He got his bachelor degree at 15 years old. His PhD degree, and he was 19 years old. When he was 20 years old, he becomes the principal of the Russian Academy of Science. He is not a Russian, but by the time the European countries are more like connected, so it's very normal, like a German guy become a principal in Russian, so on and so forth. And he actually find out a lot of or he create a lot of denotations we're actually using all these days. For instance, fx, this is for the function. This is created by Euler. And all the trigonometry related denotations, most of them are created by Euler. He's like super smart guy. And one more thing maybe you can't imagine, he is actually a handicapped person. He's like physically challenged person. 50% of his research was created when he only has one eye is functional. Okay? And the other 50 was created when he was completely blind, like Beethoven, right? When he was totally deaf and he could create like the music. And another thing, when he was 76 years old, he was actually in the lab. All of a sudden, he stand up and say, "I'm going to die." And then he fell over and died on the ground. So you really have no idea how he's pretty much like a prophet. He can predict a lot of things in the future. Okay, for Euler, his greatest contribution for the number theory actually is two parts. The first part, he proves the Fermat's little principle. This is actually proved by Euler. While the second one is he find out a lot of solution theory for the Diophantine equations. Right? We talked about the Diophantine equation before. Diophantine's a king. The king has a part-time job being a mathematician. So he spent a lot of time figure out how to find out a solution for Diophantine equation. Diophantine equation means when, okay, I just gave it an example, x plus y plus z equals to a, for instance, equals with 3, for instance, x plus y, x squared plus y squared equals with 4, for instance. You have two equations, but you have 3 variables. So normally speaking, you won't be able to find out the solution. You should have infinitely many solutions for such an equations, right? So these kind of equations is called the Diophantine equation. Like we said, normally finding a solution for the Diophantine equation is meaningless because you have so many. While if you want to find out the integer solution of a Diophantine equation, it becomes very meaningful, right? Such an equation, of course, have infinitely many solutions, but it might only have limited integer solutions. Diophantine itself and also Euler actually did a tremendous contribution in this part, finding out the Diophantine solution related theorems. Okay. Here I'd like to give you as a little bit introduction. The Diophantine equation solution, especially the integer solution of Diophantine equation, is a favorite for the high-level math competition. For instance, they can give you a weird equation for you to prove that there's only one solution for this equation, or there are infinitely many solutions for this equation. This is actually Euclid is low level, right? Yeah. From this perspective, Euclid is considered to be like a baby level. Okay, but generally speaking, that this is the Diophantine equation solution. You can basically use two important solution strategies. One is using the construction method. As long as the question asks you to prove a Diophantine equation has infinitely many solutions, most of the time you're going to use the construction method. As long as the question asks you to prove that the Diophantine equation has only one solution, most of the time you can use the just basically enumeration method. You find out the solution. And if the question asks you the Diophantine equation does not have any solution, normally you need to use the proof by contradiction method. So this is the mathematical thoughts we like to talk about in a different lecture, the mathematical thought lecture, because different like the way how the question asks you, you need to have some conditional react using different mathematical thought and strategies to solve these problems. Just want to give you a little bit as on top of this. Okay. And the last one, of course, everyone wanted to listen is the Goldbach, right? The Goldbach conjecture. That is actually a very famous conjecture. And even for today, no one find out a solution. No one find out like a rigorous proof for the solution for this conjecture. Our Chinese mathematician, Chen Jingren, he was actually the pretty much like the pioneer for this process. He find out the most advanced, the progress for the entire contribution for the entire like proof process. Okay, so this is more like a basic background knowledge talking about the number theory. And for our lecture, of course, we won't go for any of them because they're like super difficult, not to say, like the Goldbach conjecture. We're going to focus our lectures for the math competition focused areas, especially for the high school math competition focused areas. That is being said, we're going to focus on the divisibility, the prime numbers, composite numbers, the modular arithmetic, and the factor related problems, and also some very important number theory related theorems. We're going to talk about the Fermat little principle. We're going to talk about the Euler quotient principle. We're going to talk about the Chinese remainder principle. So these three principles are extremely important. And AMC likes to test them pretty much, or maybe like the same thing applies for the Euclid, the Canadian exams, likes to test them pretty much every year. So these are the focus of our lecture. Okay, so with all those information, let's jump to the first topic of our lecture, which is the divisibility related problems. And here another quick talk is that our lecture, we don't go for the, only the 8 problems rehearsals. Instead, we like to spend a decent amount of time talking about all the concepts, give you guys all the explanations, all the important things you need to know before we jump to the problems. Fish and fishing. I think fishing is more important, right? So that's the way how we organize our lecture. We all spend a lot of time talking about all those concepts first before we jump to our real problems. Before we jump to the questions, let's do some summary. Some of the most important concepts for the divisibility related topics, and we're gonna basically give you guys a refresh before we go to the real problems. First one, we're gonna talk something about the definition. What is the divisibility? I think divisibility is a basic concept. You know that from pretty much day one, okay? An integer b is divisible by an integer a. Of course, a cannot be 0. So we write as a pipe b. There's nothing but a denotation. Okay, just people in mathematics, people likes to be more brief rather than long-winded. They just use a pipe b. Means a is a divisor of b, or b is a divisible by a. It's nothing but a denotation. We can also say that it's a pipe. B is that's a vertical line. Yeah, it's actually on top of it's actually in your computer. B is a multiple. Is on top of the of forward slash, right? B is a multiple of a. Forward slash, and one of the slash. Yeah, a is like Joey mentioned, a divisor of b, right? So this is like an elementary school level question. If you have any questions, let me know. Okay, I'll send you an elementary school YouTube link that you can go back to have a quick review. A is a divisor of b. So basically we can say 2 is a divisor of 4. 10 is a divisor of 100. Right? Basic principle, nothing to say. Based on the definition, let's have some propositions. Propositions. So most of those propositions are also very intuitive. So it's not a rocket science. Most of them you can actually understand it right away. Let's try to do a little bit summary, make sure we cover all the important knowledge points. If A is a divisor of B, then A must be a divisor of minus B, right? And vice versa. If A is the divisor of B, then minus A must be also a divisor of B, and vice versa, right? So having a sign doesn't change the divisibility between different numbers. So that being said, whenever we're talking about the divisibility or number theory, most of the time we're talking about the positive integers. Without specified clearly, most of the time we're just talking about the positive integers for most of the discussion, because the negative numbers is nothing but a sign. It doesn't change anything. Second part, if A is a divisor of B, B is a divisor of C. So therefore, A is a divisor of C. Is that right? A is divisor of B, B is also a divisor of C, so therefore A must be a divisor of C. So that being said, means the divisibility can be passed on, right? The divisibility can be passed on. 2.3. If A is a divisor of B, A is the divisor of C, then A must be divisor of Bx plus Cy for all integers x and y. Right? If A is a divisor of B, A is a divisor of C, then this part, we're going to call them the linear combination of B and C. When you guys go to the linear algebra in your university, you're going to call this expression the linear combination. Why I'm saying linear? Because you see, all the coefficients are actually of degree 1. So if A is a divisor of B and C, then any kind of combination between B and C can also be divisible by A. Is that right? So for instance, 3 is a divisor of 6. 3 is a divisor of 9. Then regardless what kind of the combinations you want to make, 6x plus 9y, that must be divisible by 3. Of course, xy must be integers. Is it understandable? Right? Any combinations between, right? Linear combination between them should be divisible. 2.4. If A is a divisor of B, B is a divisor of A. So therefore, A must be either B or negative B. Two numbers, they are a divisor for each other. A can be divisible by B, B can be divisible by A. So therefore, A and B must be exactly the same, or it's only a sign different. Is that right? Okay. These are pretty much like basic things. Another one we called the quotient theorem. Quotient theorem is also very intuitive. Given AB belongs to integer, B is not 0, then there exists only one pair of integers, Q and R, such that A will be equal to B times Q plus R. Of course, the R's absolute value must be greater than 0, greater or equal to 0, lesser than B's absolute value. So this is more like you're doing a quotient, like you're doing like a quotient, right? You have a quotient and also you have a remainder, right? So here, Q is called quotient, while R is called remainder. Is that right? These are like the basic concepts. It actually means that whenever you want to use one number, one integer, to divide another integer, the quotient and the remainder should be unique. There's only one pair. It is impossible you have two quotients, two different quotients, and two different remainders. Is that right? Always, if you use a number, let's say 5 divided by 3, the quotient will be 1, the remainder will be 2, and this is unique. You can never have another pair of values rather than 1 and 2. Right? It's pretty intuitive, right? Most of this divisibility related. Okay, so a quick recap here. You might find this concept very intuitive, right? Why you have to waste our time talking about this? But you know what? Sometimes like this quotient is only one pair. you can actually use this to solve very complicated CMO or even the IMO problems. If you want to do the proof by contradiction, you construct something and you find out there are actually two pairs of quotient and remainder. Then you find like the contradiction. So sometimes the very basic concepts can be used in a very high level math competitions. Try to find out, like the rationale behind the problems. But maybe for now you don't really see that too much. So just try to understand. You guys already know that in your elementary school. So this is only a basic recap. 2.6. Some useful conclusions. The first one will say, given n and a belongs to integer, n must be divisible by a plus 1, a plus 2, a plus n. Giving n and a, they're both integers, n must be divisible by a plus 1 times a plus 2 all the way times a plus n. This is more like a mathematical language. If we do a conversion into the human language, it means that n must be a divisor of the product of n consecutive integers. Is that right? This means n consecutive integers. Is that right? N must be a divisor of the product of n consecutive integers. Is it intuitive? Anyone who can give me a very quick verbal proof? Who can give me a quick verbal proof?
Because so basically the number of remainders you could possibly have from
well, the remainder will be 1, 2, 3, 4,
all the way to
yes, go ahead.
but since the
so then by pigeonhole you have to have one of them in a plus 1, a plus 2 all the way to a plus n.
Did you guys follow Joey? Can you say that one more time?
So basically, for your module, if you take all the remainders, right?
Mm-hmm.
You have to have n has to be one of 0 all the way to n minus 1, remainder, right?
Mm-hmm.
So that's n distinct numbers, right? But you also realize that a1, a plus 1, a plus 2 also has all the remainders from 0 to n minus 1, because a plus n is also equal to 0, right?
Mm-hmm.
So then what happens is that you realize that basically by pigeonhole that the remainder that satisfies n mod a or something like that has to exist in a plus 1, a plus 2 all the way to a plus n.
Exactly. So you guys follow Joey? Yeah, that's a very good proof. It's actually very intuitive as well, right?
remainder can't ever be greater or equal to n. Eventually it's going to get up to n. Because the remainder is going to start somewhere from 0 to n, and it's going to keep on increasing, so it has to cross n at some point.
Yep, I think that's a proof. That's a proof, or something even more intuitive. You see? Think about it. Let's say if n equals to 2, for instance, any 2 consecutive integers must be one of them is a multiple of 2. Is that right? One is like an odd number, one is even number. So 7 times 8. Of course, at least one of them is a multiple of 2. Proof. Okay, there's another more. N equals to 3. 11, 12, 13. Because every 3 numbers, of course, you're going to find one number is actually multiple of 3. So all the way, every n numbers, you must be able to find out one number which is multiple of n. So n must be a divisor of the product of n consecutive integers. It's very intuitive. Is it good? So far, so good? So this is actually the first conclusion. The second conclusion is pretty much the same thing. given n, a belongs to integer, n factorial must be a divisor of a plus 1, a plus 2, all the way a plus n. N factorial must be a divisor of n consecutive numbers, their production. That part might not be so intuitive, but you guys can have a look at it. Who can give me a quick proof? Why?
Okay, it's like the proof from before, but all of the numbers from 1 to n, because n factorial is equal to n times n minus 1 times n minus 2 all the way to 1, right? So all of those have different remainders with respect to a. So therefore, each of them must, like, because by the pigeonhole, like, you can just say each of them must appear once in like a1 plus a2, because all of those also have different divisors as well.
Is that right? So regardless, like, in this problem, it starts with a plus 1 all the way to a plus 1. So regardless which remainder it starts with, right? Let's say the first one starts with 1, and then it's going to be one after another all the way to n, right? If the first one starts with n, let's say n minus 1, then it's going to be n minus 1, n, then start over from 1, 2, 3, 4, all the way to n minus 2. Right? So by any means, this remainder will be increasing or increasing to a gap and then go back increasing all the way. You can create all those n factors for the factorial, right? So that's another very intuitive proof for this thing. So you guys follow me? The other guys? The other guys, you guys follow me? I'm actually trying to prove this verbally. How are we going to do this? Fairly quick, right? Because everything is also good. Not only for n, but also for n factorial. Third one, a plus b to the power of n divided by a. So this guy, the remainder must be b. A plus b to the power of n. If I divide it by a, so this guy must have a remainder of a b. How to prove this? How to prove this?
Binomial expansion.
Is it right? The other guys? Binomial, right? You can do a binomial for a plus b to the power of n, and then every single term you're going to have a. So just forget about it. All the way you go to the last one, b to the power of n, and b to the power of n. That one divided by a will be the remainder of, that will be like base. Yeah, that would be pretty much the case. You're going to have the remainder b, right? Actually, to prove this guy is also very intuitive. Just use the binomial theorem. Try to open it. Using the binomial theorem, you'll be able to find out. Okay? Yeah, of course, a, b, n, here, all of them are positive integers. Okay? So far, so good? Any questions so far? Oh, good? These are pretty common sense things, right? Divisibility is like the most straightforward part in the number theory lectures, so we don't have too much to say. It's pretty much a very basic concepts. Okay? But let me know if you have any problems. Please let me know. The last principle you guys need to know, and then we're going to go to some questions. Principle 2.7, that's the famous number of factors theorem. That one is useful as well. Number of factors theorem. Actually, the Euclid and the AMC tested pretty much every single year. So you guys need to know this. If n can be written as P1, K1, P2, K2, all the way PL, KL. Here, P1, P2, all the way to PL are prime numbers. Okay? I basically give you the prime factorization of n. Okay? A prime factorization of n is already given. Then, all the factors of n can be written as big N. Big N means the total factors of N is actually equal to K1 plus 1, K2 plus 1, KL plus 1. I'll let you guys finish the writing first. This is the famous number of factors theorem. If given N, I already present you the prime factorization, P1, K1, P2, K2, all the way to Pn, K, PL, KL. If I want you to calculate the total number of all the factors of N. So whenever I say all the factors, it actually means including 1 and N. They're all included. Are both included, sorry, not all. Both included. It means that all the factors, 1 and N itself, everything all together, the total number should be this guy. All the exponents plus 1, and then multiply them together. I'll give you an example for this to make it easy. For instance, 36 actually equals to 2 to the power of 2, 3 to the power of 2, right? So according to our number of factor theorem, the total factors of 36 should be 2 plus 1, 2 plus 1, which is 9. Is that right? Actually, the total factors of number 36 are actually 9. They are 1, 2, 3, 4, 6, 9, 12, 18, 36. Okay? So I think the proof for this theorem is not so difficult neither. Who can give me some idea? Who can give me some how to prove this principle?
It's just like the combinatorics question, because you just have to choose how.
Wait, did he cut off?
Oh yes, no, it's good. Yeah, I cut it off because somebody want to give some explanations how to prove this.
Oh, basically it's combo, and then by fundamental theorem of arithmetic, since each of the factors can also be written as a unique like prime factorization. So for every possible power, like you can like decrease it to like 0 to n, so then that would give you n plus 1 like powers, right? And then you multiply each of those by combo, and then like you would get the formula.
Is that right? So for each prime factor, this is more like a counting. This is more like a counting problem, right? If we're talking about each specific factor, let's say for P1, I have the option to choose 1 P1, 2 P1s, all the way to K P1s, or I can choose 0 P1s, right? So talking about the factor P1, we have K1 plus 1 different scenarios, right? Same thing applies for P2, all the way same thing applies for PL. So the total scenarios, this is more like a multiplication principle, right? The total scenarios will be the multiplication for each factors from P1 all the way to PL. Is that right? So that's the reason why this K1 plus 1 all the way to KL plus 1 comes from. Any questions? All good? Okay, if all good, let's continue.
How many of each prime you want, and you're just asking how many different ways can you choose those primes, and where you can choose no primes or as many primes as you want.
Yeah, it's pretty much, right? So basically, if you want to decide all the factors, for the first one, you can choose 1 P1, 2 P1, all the way to K1 P1, and also 0 P1. So that's the reason you have K1 plus 1 for all the P1 related thing. And the same thing for P2. You have K2 plus 1, all the way KL plus 1. It means you just basically take all the PLs or no PLs. And then you're going to use the multiplication principle, right? In order to finish your job, you have multiple steps. You have L steps. So that's the reason how to multiply them together, right? So that's the basic proof of the principle. Okay? I think like for the divisibility, the basic concepts are fairly straightforward. You guys should already know this from day one. So I'll be surprised if you are totally like black out for all those kind of concepts. So I think it's good for us just basically sit down together. I will give you guys some quick just walk through for all the principles related in the divisibilities. Any questions? So far, so good? Okay. Because moving forward, we're going to do the same thing for the other topics. We're going to go through all the concepts first, all the important conclusions before we jump to the problems. All right, I think this is more efficient. If so far so good, let's go to some practical questions. Let's go to some practice questions to see how we're going to use how we're going to use all those principles we introduced before to solve the problem. Okay, again, every single question, I want you guys to show me how do you think rather than the solution itself. Let's go to a question number 1. This is a warm-up question. Even A, B, N belongs to the positive integer. For any given K belongs to the positive integer. I think everyone should know this, right? This A, like upside down, means for any given. Just like it's actually from the word arbitrary, but people just make it, you know, the mathematicians like to make easy things difficult. So they like to just upside down like the word A, arbitrary, to make it as this, for any given K. Any given K belongs to the positive integer. We have B minus K is a divisor of A minus K to the power of N. Okay, so please prove. B minus K should also be a divisor of A minus B to the power of N. Give you 3 numbers A, B, C, A, B, N. They're positive integers. And I give you guys a condition. B minus K is a divisor of A minus K to the power of N. And here I wanted to prove also B minus K should be a divisor of A minus B to the power of N. Okay. A question like this, how do we get started? How do we think? Well, always we're going to start with an observation, right? Oh, the old student, like the old mates should understand where I come from. We're going to start with observation. Basically, the positive integers, there's nothing. They only give you one condition. You need to use this one condition to prove another condition. The one condition is B minus K is a divisor of A minus K to the power of N. And you need to prove that B minus K is a divisor of A minus B to the power of N. The good part is the divisor part are the same, right? So there's nothing you need to do for the B minus K. The only difference is here. A minus K to the power of N, A minus B to the power of N. For sure, I need to find out the relationship between the right-hand side, of the pipe, right? The right-hand side of pen. So your observation tells you that you need to find out the relationship between A to the power minus K to the power of N and A minus B to the power of N. Right? As long as you find out the relationship between these two guys, you might be able to solve the problem from there. So this relationship is not so complicated for sure, right? If I write it in this way, this guy will be written as this guy, right? It's a quick It's a quick tweak. Looks like that's pretty much what I can do from here, right? And think about it. This is what I need to prove. This is what I already have, right? This is b minus k is a divisor of a minus k to the power of n. The only difference part is this part. Who can think about it? I just need like a one-step thing. This is like a warm-up question. This is not a super difficult question, right?
Just factor out the n, like put the n and the outside the brackets, and you get b minus k and bracket to the nth power. And since it's just a power of the original thing, it's obviously a divisor.
Exactly. You guys follow Edward? Yeah, like I said, yeah, that's actually like the right answer. So let's have a quick observation. Okay, let's have a quick observation. What we need to do is that b minus k need to be divisible by a minus k to the power of n, right? This is what we need to do. What I have already is here. b minus k is the divisor of a minus k to the power of n. The only thing I don't know is here. You see, they all have the b minus k thing here. You see, let me change a different color. B minus k, b minus k. So these two guys are both a multiple of b minus k, right? As long as I can prove this guy is also a multiple of b minus k, I'll be able to solve the problem. Is that right? This is exactly what we used before. Do you still remember? If A is a divisor of B, A is a divisor of C, then A must be a divisor of all the combinations between B and C. Is that right? If A and B, they are a divisor of B and divisor of C, so A must be a divisor of all the combination of B and C. So for now, this is going to be my B. This is going to be my C. If I can find out B minus K is a divisor of C, plus B minus K is already a divisor of B. So B minus K might be whatever combination between B and C. You guys follow me? Right? This is like a basic observation. You always need to find out the solution based on your observation, and you're not using a super complicated theorem. Okay, so the thing is, how can I prove B minus K is a divisor of B to the power of n minus K to the power of n? Pretty much everyone knows that, right? This is a famous factorization you guys need to remember, right? Because b to the power of k minus b to the power of n minus k to the power of n is actually equals to b minus k, bn minus 1, bn minus 2k, all the way bk minus 2, k n minus 1. Is that right? This is actually one of the propositions from the binomial theorem. You guys need to remember this part. This is actually common. Very important. You need to know this. You need to know this, okay? So this part you need to remember. And the other part is x to the power of n minus 1. You can actually use the same thing to do xn minus 1, xn minus 2, x 1. So these two expressions, factorizations, please try to remember. Okay? It's the favorite by the math competition. Okay? So this is like a warm-up question. It's not so complicated. As we can see right away, okay, so how are we going to do this? Because, let me do a proof. A brief proof, the writing is actually very because important. We already know that b minus k is a divisor of b to the power of n minus k to the power of n. B minus k is also a minus k to the power of n. So therefore, b minus k must be A, B, A, right? A combination between the two parts. That being said, is A to the power of n minus B to the power of n. Okay? You're just using a simple, very simple principle, and you get what you need. So far, so good? Try to brief your
Yes or
writing.
no?
Don't write
So
too
good?
long. I know some students, they're Euclid,
Okay.
write like so many
So
pages.
let's go to another question. A little bit more difficult
One-liners,
compared with the warm-up question. Question number 2. This is a 1989 Amy problem. Trust me, even though it's an Amy problem, it's 1989 Amy problem. For now, it's almost like a Euclid problem because our complicity is going exponentially, right? 1989. I think I showed you guys 1970 something IMO problems. So easy, huh? IMO problems, 1970s. It's almost nothing these days because unfortunately, like the big trend is going up exponentially, more and more difficult. Even though it's Amy, but I think it's almost like Euclid. It's a Euclid level. Not even like the last question in Euclid. Maybe like the, like last 2 or 3 questions in Euclid. Okay, the question goes like this. If A is lesser than B, lesser than C, lesser than D, A, B, C, D, E, 4 letters actually. Oh, I mean 5 letters, excuse me, 5 letters. B, C, D, their sum is perfect square. A, B, C, D, E, their sum is perfect cube. These 2 informations. If A lesser than B, lesser than C, lesser than D, lesser than E, they are consecutive positive integers. Just 5 numbers in a row. Okay? Such that B plus C plus D is a perfect square. A, B, C, D, E, all the sum is a perfect cube. So what is the smallest possible value of C? There are some common sense for this problem. That's the reason why I like to bring up this problem. Okay. So listen to the analysis. Again, let's focus on, there are some tricks, there are some patterns, there are some formulas we need to follow. Okay. Part of the important part of the lecture is to teach you guys what is the formula. There are 2 common things, common sense things you need to remember in the future. First, whenever you have a consecutive numbers, who can tell me what is the first reaction? What are like the basic properties for the consecutive numbers? What is the base? Yeah.
You only really have one variable. So like in this case, you could just put everything in terms of C.
You guys follow Alan? Is that right? Consecutive numbers, your first reaction is they are arithmetic sequence, right? Arithmetic sequence. So let me write it down here. Consecutive numbers, they must be arithmetic sequence. Talking about the arithmetic sequence, you're pretty much seeing the number in the middle, right? They're talking about the number, they're talking about the numbers in the middle. So B plus C plus D is actually 3C. A plus B plus C plus D plus E should be 5C. Right? This is a common sense. You guys should always remember. Consecutive numbers is always a arithmetic sequence. Plus, the question is asking you what's the value of C, which is quite aligned, right? The question asks you to determine the value for C. Of course, you're going to do your problem using C. You're going to get rid of all the other irrelevant numbers, right? All the important numbers are the C. Okay, that's it. 3C, 5C. Trick number 1. Consecutive numbers always do this arithmetic thing. Trick number 2. As long as the question say blah 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 is a perfect square, blah 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 is a perfect cube. If you say this is a perfect square, okay, I'm just gonna denote this guy using a perfect square. If you say this is a perfect cube, I'm just gonna denote this guy using a perfect cube. This is a common practice, so, try to remember, okay? Perfect square, cube, denotation, okay? If this is perfect square, I'm just gonna put m square. I don't even know what is m, but I'm just gonna put m there. If this is perfect cube, I'm just gonna put n there. Later, we're gonna give you guys some basic properties for the perfect square and perfect cube. For instance, I'm just gonna give you one thing. For instance, a perfect square, if you use the perfect square to divide a certain number, the remainder should be always limited. Later, I'll give you guys more information. Like perfect square, if you want to divide 10, it won't be to have like certain amount of, like so many remainders. It's only a certain remainders. So those things can actually help you to do the analysis in the future. Okay? Yeah, that's like the modular table. Because like the modular, later we're going to go to the modular, we're going to expand too much. We're going to expand a little bit, not too much, a little bit. Like, because the modular, actually some modulars have some properties, some patterns. So let's say a perfect square, like the last digit of a perfect square, it won't be an odd digit. There will be a certain amount of digits, can be a last digit of perfect square, so on and so forth. Later, we're going to go to it. But for today's question, this is under the divisibility territory, so we won't be using that part too much. Okay, just a quick comments. Yes, for the number theory, there are so many interesting conclusions you need to remember. Those interesting conclusions is going to help you to do the enumeration in the difficult problems. Let's say what I'm talking about is that the last digit of the perfect square, they can't be random numbers, right? So whenever you see some problems, you have a perfect square, try to do enumeration. Sometimes you're going to do an enumeration for the last digit. And if you know this in advance, you don't have to waste your time. Check all the digits, and pretty much some of them is already there. But we'll talk about it in a future lecture. Okay. Yeah. As long as you know this, the next trick is, you see, I'm just going to change a different color to here. Now you have what? 3C equals to 3C equals to m squared. 5C equals to n cubed. Let me ask you something. 3C equals to m squared. So that being said, 3 must be divisor of m squared. Is that right? Two numbers, their product is the divisor of m squared. At least one of them, I mean, 3 times c equals to m squared. Of course, 3 per se should be a divisor of m squared. Is that right? But I'm not really stopped to m squared. If 3 is a divisor of m squared, then I will say 3 must be divisor of m. Is that right? Can you guys follow me about this? If 3 is a divisor of m squared, then 3 must be a divisor of m. Why? Because 3 is a prime number. There's no way for you to decompose the prime number, right? If m squared has 3, then M must have 3 as well. Right? There must be like 2 3s inside M. Is that right? So that's the beauty for prime number. But it doesn't work for a composite number. Right? A composite number not necessarily correct. But a prime number, it does correct. 3 must be, if 3 is a divisor of M squared, of course, 3 must be a divisor of M itself. Right? Guys follow me? Okay. Let's just continue in this part first, okay? I'm just going to erase this. Okay, let's continue this part. If 3 is a divisor of M, of course, M can be written as 3k. Right? This is a common sense, right? If 3 is a divisor of M, then M, of course, can be written as 3k. Now we're just going to put it back. You're just going to put it back. So 3c equals to 9k squared. Is that right? Because your goal is trying to find out C, not trying to find out M. You don't care about M, you care about C. Is that right? So that being said, C is actually equal to 3k squared. Is that right? Okay, follow me this pattern. This pattern is extremely important. This is the pattern. 3c equals to M squared. 3 must be a divisor of M squared. Because 3 is a prime number. There's no way for you to chop it. You can no longer chop it except you chop into 1 times 3, which means nothing. So therefore, 3 must be a divisor of M. As long as you know 3 is the divisor of M, put it back. M equals to 3k. And then all the way, because your goal is trying to determine the value for C, not for M. So what you care about is C. So therefore, C will be equals to 3k squared. See, from here, we all the way go to here. This is a very common trick for the number theory related discussion. This is an easy problem, but try to understand that. Let me do another one, okay? Just as a practice. The common pattern for most of the problems. 5c equals to n cubed. So that being said, 5 is a divisor of n cubed. Right? If 5 is a divisor of n cubed, because 5 is a prime number, there's no way for you to chop 5 anymore. So therefore, 5 must be a divisor of n. This part is a little bit not tricky, but you guys need to be familiar with this analysis. So let me stop from here. So basically what I can say that as long as I have a prime number as a divisor of n to the power of whatever, I can basically say that the prime number will be a divisor of the n itself. Is that right? You guys follow me? A prime number is a divisor of n to the power of whatever, I don't really care. I can basically say that this prime number will for sure be the factor of that n itself. Right? This is one of the prime number composite number properties. We will cover this later in the lecture. If prime number is a divisor of n cubed, n squared, and whatever, prime number must be a divisor for the n itself. Guys follow me? A prime number is a divisor of n's exponent, whatever exponent, then prime number must be a divisor for the n per se. Same thing. If 5 is a divisor of n must be equal to 5, not 5k, let's change a different one, 5l, for instance. Is that right? So put it back. 5c equals to what? 125l cubed. So therefore, c will be equal to 25l cubed. Is that right? Of course, k and l, they're positive integers, blah, blah, blah. I don't have to mention too much. Because like I said, by default, we're only discussing the positive integers. Okay, now we have here, c equals to 3k squared, c equals to 25l cubed. Don't forget where we come from. Our goal is trying to calculate c. Right? Don't get confused. Don't get lost during your calculation process. Your goal is trying to determine what is the value for C. So therefore, That being said, you need to find a smallest c such that c can be written as 3k square, 3k square, and also c can be written as 25l cube. Who can tell me? Who can just help me determine what is the value for c?
I got 5 squared times 3 to the power 3.
Yep. Can you
That's
elaborate?
675.
You see? Okay. 675. Right. Right. Exactly. Right. So what are you going to do? You're going to do this, right? You need to find out some c, right? It can written as 3k squared and also can be written as 25l cube. You don't have to do a lot of math here. Just trying to squeeze out something, right? You need to find out something, maybe something for k, something for l, and make sure this equation stands out. That's it, right? Just try to find something. You don't need a lot of like calculations. Just try to find out, try to find out, guess out some numbers, the minimum numbers to make sure this equation holds. It's not something so difficult. If L equals to 3, K equals to 5 times 3, you're going to have what? 3 times. Is that right? So you can make sure this equation holds. So this part, you don't need a lot of like deep mathematics knowledge. Just doing a little bit of observation, analysis, whatever you name it, you can find out, you see, you're going to have this and you're going to have this. The left-hand side part, the right-hand side part, you have a square and you have a cubic, right? Basically times them together, you get what you need. So far, so good? So far, so good? Any questions so far? We're trying to use the simple problem to reflect a very important mathematical thinking. So try to, try to get a beat, okay? Okay, if that is the, okay, if so far so good, let's have a quick recap, okay? In this question, we basically want you guys to remember two things. Things number one, whenever you see a consecutive numbers, think about the arithmetic sequence. Arithmetic sequence, you care about like the one in the middle, right? Second part, as long as the question says something is equal to a perfect square, something is equal to a perfect cube, no worries, just try to do a denotation, put them there. Perfect square, perfect cube. And whenever you see something like this, trust me, in the future, try to use what I told you. If a prime number is the divisor of a certain number's a certain amount of exponent, so the prime number must be also a divisor for the number itself. You don't have to worry about the component. Okay? But that's only for the prime number. It doesn't work for the composite numbers. So far, so good? Any questions? All good? Okay. If all good, let's go to another question. Question number 3. I'm going to write out a question, and we're going to go for a break. Hopefully, somebody can give me the answer after the break. We'll see. This is a 2003 Chinese Western region MO question. No, this is not super difficult. China is big. A relatively easy west problem. To the east, they have their own regional MO, and then get together at Beijing to have like the real Chinese MO. No worries. Something like this. Given, if you go to the mathematical thought lecture, they're all Chinese, Russian, Ukrainian problems. They're pretty much come from them. 8 positive integers. And in our assignment, I gave you a lot of Russian, of the weird countries MO problems. You can check it out. Let you guys finish writing first. Given 8 positive integers from 1 to 8, you like to place them on the 8 vertices of a cube. So you have a cube, right? You have 8 different vertices. You just like to place them on the 8 vertices of the cube. But you can't do them randomly. You have to do that in a way such that the sum of any 3 given numbers on the same face. Let's say for this face, it has like 6 different faces, right? For any 3 numbers on any face, the sum of them must be greater than 10, right? You need to have some kind of combinations, placement, make sure that happens. Okay, if you already done such a placement, so tell me, what is the minimum sum of the 4 numbers on the same face, right? For now, because the question say the 3 numbers here must have a minimum more than 10. But my question for you is that if I calculate the 4 numbers on the same face, what is the minimum for 6 different faces? You guys follow me for the question? Right? 8 numbers randomly put in a cube, and any 3 numbers on the same face must be greater than 10. And please, in such a situation, please determine what is the minimum sum for the 4 numbers on the same face. So this question, for sure, you're going to use some enumeration, right? We talk about enumeration. Sometimes counting on probabilities, number theories, enumeration, they're pretty much bind. They don't really, there's not a very black and white like lines between them. So sometimes all the number theory problems, you can either do some counting on probability, some counting, or you can do some enumeration. There's like the boundary is pretty blurred between these two concepts. Okay, so I'll give you guys some hint. We're going to do some enumeration and think about it. How to use the condition given by the question, more than 10, to determine the last one. Okay, this is like a filling the blank question. So this is not a big question. So like the solution should be fairly quick. Think about it, and we will review the answer after the quick break. Okay, let's go for a 10 minutes break, and then we'll resume afterwards. Do you guys want to go for a break, or we just continue? Hi guys, are you still wake up? Okay. I'm just gonna make it fast. And Alex, they're quite aligned.
C and D, or the 4 vertices, sorry. And then without
our squid, like without the loss of generality. Okay, just bear with it. Just for a sec. Anyone have any ideas? Just before we jump to the solution, who can just elaborate a little bit? What is the big direction for us to solve these problems? Think about it. You have, yes? Does anyone want to talk something?
Wait, is the answer 13? Or am I off?
Quite close, but not 13.
Oh, okay.
It's actually 16. 16.
Wait.
But think about it. Who can? Yeah, I think like same thing with David. David gave like 13. Yeah, I think there should be something very close. Maybe who like to elaborate a little bit?
Oh, I know.
It's quite close, right? It's quite close. Well, the most important thing is you don't have to do a hard enumeration, because the hard enumeration doesn't really help you too much, right? You can use some analysis plus the enumeration to help you out for the problem. And that's the $1 million part for this question. This is not a super last two problems. Like this is pretty much like a first one or two problem. But think about it. Whenever you see a condition like this, three numbers, they're like what is called like three numbers, their sum is more than 10. What does it mean? How can you convert it into a more enumeration or like counting related condition? Who can tell me this? Think about it. We need to convert our condition into something tangible. Three numbers greater than 10, it doesn't really make sense. But we need to somehow figure out that how can we convert it into a mathematic language? Because we actually care about like the last one as well, right? Like the fourth one as well. Kind of build up the relationship. Do not always go for the pure enumeration. Look at a face with 1, okay? No worries. Let's go to the solution. And if you have something sparkling, you can let me know. We can pause the solution. Okay? So this is like an interaction process. Think about it. We just find out maybe we have such a face, which has A1, A2, A3, A4. Okay? So in this phase, you're going to have like maybe A1 lesser than A2, lesser than A3, lesser than A4. It doesn't matter, right? This phase, we should have the three minimum numbers. Their sum is greater than 10. A1 plus A2 plus A3 greater or equal than 10, right? That's actually given by the question. So the question is pretty much, please tell me what is the minimum sum of the four numbers on the same phase. It looks like if these three guys already reach the minimum 3 sum, maybe these four guys can reach the minimum 4 sum. 4 sum. Is it right? Maybe. I didn't say must. Maybe. Because the 3 numbers goes to the minimum 3. Yeah, this is not a good word. Yeah, I see somebody. I'm sorry about my wording. Yeah, there's like 3 number sum, right? So like the minimum. This is like the minimum of the 4 number sum. Yeah, this is really bad. 4 number sum. So yeah. So, but there's no guarantee. Maybe there's not maybe like the number 4 here is like too big, right? So if you're adding this 4 to the existing 3 number sum, it's basically breach like the smallest 4 number sum. It's okay. We can always get started from there. A1 plus A2 plus A3 is greater than 10. So that being said, who can tell me, is there a constraint for ABC? ABC I should take from whatever numbers to make sure that A1 plus A2 plus A3 is greater than 10. Yeah. So my question is that maybe ABC, A1, A2, A3 cannot be so random, right? You need to have some kind of like some constraints to make sure A1 plus A2 plus A3 is actually equal than 10, is actually equal or greater than 10. Who can tell me? What is the constraints for A1, A2, A3 such that A1 plus A2 plus A3 will be greater than 10?
A3 has to be either 5 or greater.
Is that right? So 1, 2, 3 cannot be too little. 1, 2, 3, it doesn't make sense. So that actually means A1, A2, A3. If I do a sum, if I do a set, these guys will be actually, all of them should be greater or equal to 5. Is that right? So far, so good? Okay, our goal is trying to find out A1 plus A2 plus A3 plus A4. What is the minimum? Right? Then who can tell me what is the minimum for A4 now? Because I have already used 1, 2, 3, 4, 5 already for the 1, 2, 3, A1, A2, and A3. Is that right? So that being said, there's not so much options for me for the A4. A4 must be greater or equal to 6. Is that right? Because A1, A2, A3 already takes 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So the minimum I can do for A4 is going to be A4 equals to 6. So that being said means I can have A4 greater or equal to 6. Do you guys follow my analysis? I don't really put the numbers yet. I'm just trying to do some brainstorming. Because A1, A2, A3 already takes 1, 2, 3, 4, 5. Right? It can't be too small, it can't be too big, but it must be greater or equal to 5. So therefore, A4 must be greater or equal to 6. So that being said, A1 plus A2 plus A3, this guy greater or equal to 10, right? A4 greater to the 6. So A1 plus A2 plus A3 plus A4 should be greater or equal to 16. But this is only my brainstorming. This is my imagination. I think I should have such an A4 such that A4 can be greater, just equal to 6. Well, the other three numbers we go for like whatever. So the total number will be greater than 6, greater than 16. So I think you might have such an answer, which is greater or equal to 16 as the minimum. But I have to give you the case. Right? I have to list out like the real case before I can wrap it up. The real case, I actually have it here. Because you know what? If you only have this inequality, there's no guarantee that you can really find such a pattern, right? The inequality just give you theoretically, you might have this number add up to more than 16, but there's no guarantee you really have such a pattern. So it is always important you need to print out such a scenario to make sure
I'll
this
show
pattern
you
does
how
exist.
this real arrangement works.
You're going to have 1, 4, 5, 6, 8, 7. Okay, that's like the number you're going to have. So that's the one you're going to see from here. So this face is going to give you the 16, which is the minimum. Or the same thing according to Edwards' calculation, right? It's the same thing, right? He figured out C must be greater than 4, so therefore D will be equal to 6. For my case, this is D, right? D will be equal to 6, so therefore all the sum will be 16. Is it good? So far, so good? Any questions? Please let me know. This part is you need to do a conversion from a pure, from a pure language Edwards solution is also good. You can just copy paste the Edwards solution. It's the same thing. For me, I basically do analysis for A1 plus A2 plus A3 greater than 10. So I squeeze out A4 must be greater or equal to 6. Put them together, you're gonna have 16. Andrew Edward collaboration solution. Yes, so it's like the same thing, right? But you know what? Sometimes it's always important you present it. In terms of like in the academic world, if you only speak it, but you don't publish a paper, so like the Nobel laureate is going to go for it's going to go for the guy who write a paper. So it's always important to publish what you write, not only But our lecture we don't do. Our lecture we will promote you guys to more speak. Speak is faster. Writing is going to take forever. So far, so good. If all good, let's go for the last question for today's lecture. This is question number, is it number 4, number 6? Number 4, yes. This is a 1997 Ukrainian Mathematics Olympia practice question. Ukrainian, so Eastern European countries are very good at this mathematics, right? From the Russian, Romanian. Romanian is the first country in the world who generate the high school math competition. Before that, there's no high school math competition. Romania is the first country basically generated, and all the Eastern European countries basically follows. Question is proof. Regardless how many 3's are inserted between the two zeros in 12008, the result must be divisible by 19. Okay. Like the question per se sounds like a Math Olympia question, right? Yeah, I'm just gonna pause it for a while. By 19? Yeah, so I'm just gonna pause it for a sec. This kind of problem is actually very common in the high-level math competition. You have a series of numbers, you keep getting keep inserting numbers into certain bits, and then they're gonna say, okay, this number will be divisible by a certain number. Or some problem says, there's a number like 12008, I'm gonna insert 100 3's between two zeros. Please prove that the final number will be divisible by, I don't know, 13, 20 or something. Of course, it is impossible to do a huge calculation to see, okay, if I put like 300 3's between two zeros, no. You have to find out a way, like an induction way, how to do this. So this problem, like the reason what I'm putting here is any problem like this, we need to use the induction, like the induction way to do it. You can't directly jump to the number they're asking you to do the divisibility. Okay, so brief. It gives you something quite understandable, but quite difficult to put them into the math language, and you don't even know where to get started. Regardless, how many 3's are inserted between the two zeros in 12008, the result must be divisible by 19. It means what? So if I put 1 3, 2 3's, 3 3's, regardless how many 3's, 1 2 0 3 3 3 0 8, right? And 3's between the two zeros, the result will be always divisible by 19. Okay? Let's think about it. A question like this, what are we gonna do? How are we gonna do?
I was thinking like putting it into like base 19 and seeing what happens, because like a lot of the questions where you try to find divisibility rules like for 3 and things like that, you put into base 3 to find those rules. So I think maybe like trying that for 19 might work. Okay,
that's a very good direction. Who else? Some brainstorming. There's no bad answers. Right? So what do you guys want to say? What is the approach for such a problem?
Apply the divisibility rule of 19.
Mm-hmm.
And then use
the divisibility rule of 19. Okay, yes, go ahead, yes.
And then use induction to prove that it will always be divisible by 19. Because effectively what you're doing is taking the number, subtracting by 3, dividing it by 10, and then adding 6. So then you can prove that that function, if the previous number was divisible by 19, you prove that function also gives a number that's divisible by 19.
Okay, so the $1 million question is, what is the divisibility rule of 19? Yeah, I think David has the same concern. What is the divisibility rule of 19?
You truncate the number and then you take you truncate the last digit and then you multiply it by 2 and add it to the rest.
You
You can
guys follow
prove it
Joey?
because you know that 18 is equal to 9 times 2, right? And you know
Mhm.
19 is equal to that plus 1. So
Mhm.
then basically what you can do is like you can manipulate the numbers such that because 18 is equal to 9 times 2 and 9 is equal to 10 minus 1, right?
Mhm.
So then you can like use some algebra to find out like if this
Okay.
number is divisible by 19, then the
Okay.
truncate the number is divisible by 19.
You guys follow Joey? So Joey want to figure out a way how to determine certain number is divisible by 19. And moving forward, yeah, let's say somehow we figure out like the rules. Well, moving forward, the next step is doing what? Induction, right? Is doing the induction. We're trying to see if the number works for, I don't know, for n minus n threes in between. So it should also divisible for the next number in the sequence. The next number in the sequence will be n plus 1 threes in between. Is that right? That's what you say, Joey?
Yeah.
So you guys follow Joey? So the induction is actually the only way to solve this problem. You can't really do a direct solve, right? You're going to find an induction. You're going to get started with something easier and then all the way find out a relationship in between. And this is a very common practice for the MO-related problems. Okay, so let's have a look. Let's have a look about my solution, and we'll take it from there. If you call the insurance company and say there's no bad questions, and now there's no bad answers. Yeah, there's no bad answer. Think about it. You can always let know that. Yeah. Insurance companies say there's no bad questions, right? Here's no bad answers. So we need to think about how we're going to figure out like the 19 thing. Well, the most important thing is that we need to figure out. At the very beginning, I might ask you, I think we should go for a question, like $1 million question is do the observation, right? Before we jump to the solution, we always start with the observation. You guys should be pretty much asking yourself a question. Why 12008? Why divided by 19? Right? There must be some reason behind it. Like we keep saying from day one, every single math competition questions, every single number that's specially designed, like the number given to you must be there must be the reason behind it. It's not like randomly give you some numbers, have fun. Why they choose 12008? Why they're talking about divided by 19, not 91? Something like that. There must be some reason behind it, right? If you figure out the reason, you solve out the problem. That's like the first question. The second question I will ask you guys, maybe this is pretty much like a pattern. In the future, if you see any question goes like this, add a number in between, add two number in between, add three number in between, add whatever number in between. So this is more likely you're creating a sequence, right? Adding 0, no threes is the first term. 1 3, second term. 2 threes, 3 threes, all the way whatever threes. So you're pretty much dealing with such a sequence. This is the important part. You're actually constructing a sequence, right? You can't solve the problem by themselves, but creating a sequence, you can use in the method. Right? You can use in the sequence. You're somehow trying to prove that all the terms in this sequence is divisible by 19. Is that right? You guys follow me? So by saying this, I'm not doing this for fun. I'm just teaching you guys how to do a transform from a human language into mathematics language. Previously, we were saying at 1, 3, 2, 3, 3 threes, whatever threes, it works. That's like a human language. You can't write too much human language in like whatever, right? You need to put it into a mathematics language. Mathematics language will be able to guide you, or at least you can play around with the mathematics language. So the mathematics language becomes pretty much like this. I have a sequence all the way to whatever. I want to prove every single term in this sequence is divisible by 19. Okay. Before we go to anything, let me ask you a question. If I want to ask you guys to prove a sequence-related problem, there's one important method you need to always remember. Always and forever. Which method? Who can tell me? The Gabriel has the right answer. Induction. Is that right? You guys all know the mathematical induction method? Mathematical induction method. If you guys know shy, you can chat to me privately, then I will elaborate a little bit. I'm asking all you guys. If you don't understand, you can chat privately to me. I will see you. No one else will see you, but I will give some explanations. Otherwise, I'll just directly jump to the following solution. Mathematical induction method. All good? You guys all familiar with mathematical induction? Mathematical induction, how many steps? Are you guys all familiar with mathematical induction? Can you let me know? Okay, most of the guys does not really know the mathematical induction. So, okay, and some other guys know, like 50-50, yes. So, okay, I'm just gonna give many steps for the mathematical induction method? I'm just gonna random ask somebody, okay? Maybe this time, so I'm just gonna zip it a little bit. Mathematical so you can just let me know. So therefore, I'll show you. I'll make it short, okay? Not a super long thing. Mathematical induction method is a very important method. We covered it before for our sequence and series related topics. Something like this. In order to prove something, this is a very important method. You're gonna prove something in the sequence. Something holds, like an equation holds, like whatever. You always go for 3 steps. Step 1, you let n equals 0 to verify the condition holds. I'll give an example. For instance, I want to say 2k plus 1. I just say that randomly. I say 2k, maybe 2k squared plus 1 is always can be divisible by I don't know, by 7. I just give something randomly. Okay. If I say please prove 3k plus 1 is always a divisor. It's always divisible by 7. Okay. Regardless, k can be 0, 1, 2, 3. K can be 1, 2, 3, all the way to whatever. Maybe 1 doesn't look so. Maybe 4. 3 steps, okay? 3 steps or 2 steps. 3k squared plus 1 is always divisible by 4. For instance, I like to prove this. You always go for 3 steps. Step 1, let k equals to 0. You validate the condition, which is easy to put it there, or k equals to 1. In our case, I just want to give you some easy, like k equals to 1. Okay. Step 2. Suppose when k equals to m, the condition holds. You need to prove, just to prove, when k equals m plus 1, the condition also holds. So step 3, therefore, when k equals all the positive integers, the condition holds. Okay? So this is basically how this mathematical induction method works. Okay? In order to do something, you basically go for 3 steps. Step number 1, when k is equal to m, the condition holds. Step number 2, prove whenever k is equal to m plus 1. Suppose when this k is equal to m, this condition holds. And you don't have to prove, you just suppose this condition holds. And then using this condition to prove when k is equal to m plus 1, the same condition also holds. So you will be able to prove whenever k's belong to whatever positive integers, the condition holds. So this is the mathematical induction method. If you guys don't know, I'll send you guys some link. You can have some quick understanding. So this is more covered for the sequence and series sections. So here we're just going to use it. But this is not like the most important focus of our lecture, of our current lecture. But this is a very important methodology you need to remember. So that actually means that, just like Gabriel said, if you want to use the mathematical induction method, then we need to find out such a sequence, right? Using the mathematical induction method for the sequence. And the most important thing is I need to find out the general formula of the sequence. Is that right? If I know the general formula, I can basically play with the general formula. I'll be able to determine if all the terms can follow the condition, so on and so forth. You guys follow me? Find out the general formula of the current sequence is actually something very important. You see, looks like Edward is like he can be, he's basically types whenever I'm speaking. Yeah, we're trying to make sure. So Edward, don't type too fast, right? You're typing too fast. I can't follow you. Yeah. So let's continue to see what we're going to do for this. So this sequence actually have 2008, 2038, 1, 2, 3, 3, 0, 8, all the way to whatever. Okay. So first thing first. The question says, regardless how many threes you put it into the sequence, you're going to always have a number divided by 19, right? Let's have a quick look. Even the first term is also divided by 19. Okay? Even the first term, without putting any zero, regardless how many threes, 0 is also considered to be like a scenario, 0 threes, right? The first one is divided by 19. The second one, also divided by 19. The third one, also divided by 19. You see, even for the quotient, kind of having the same trick, right? You're adding more threes in the middle of the quotient to make it more, goes up. Like I said, every single math competition question, especially designed, every number given for you is not a random number. There must be some reason. So I'm kind of having a sequence. This is A1, this is A2, this is A3, whatever, right? You want to prove AN is divisible by 19, right? Okay. So it looks like the $1 million question is that I need to find out the general formula, or at least a relationship between my different terms in order to let me continue, right? To let me continue. Who can tell me, by just like doing some observation, who can find out what is like, maybe it's kind of like difficult to find out a general formula, right? It's a little bit difficult. But who can find out the relationships between each other, like adjacent two terms of the sequence? If we don't have a general formula, then maybe we go for recurrence formula. For sequence we have two formulas. General formula is like the relationship between n and an, right? An whatever equals to 3n plus 1. This is a general formula. Let's say an equals to a1 plus n minus 1d. Right? Let's take arithmetic sequence for instance. This is a general formula. Another formula is also very important. We call it the recurrence formula. Recurrence formula is the relationship between a1 and an minus 1, an minus 2, an minus 3, whatever. So for the arithmetic sequence, the recurrence formula is an minus 1 equals to d, right? Because it's the common difference. So maybe find out the general formula is a little bit too difficult. Who can help me find out some recurrence formula? Who can tell me what is the recurrence formula between this whatever two terms? A1, A2, A2, A3, A3, A4. Is there any relationship between those like different terms? if you want to do the induction method, you need to find out the relationship between the two terms, right? So that's the reason why I want you guys to think about it. How can I get a relationship between two terms? Yeah, you see? Gabriel already has the answer. AN is actually equals to 10 times AN minus 1 plus maybe 19 times 12, right? 288 equals to 19 times 12. Is that right? 288 or 220, yeah, whatever. 19 times 12. If you guys can't really get it, it doesn't matter. You know, most of the question like this, you don't need to have something so rigorous. Just try to do something, you know, list out some scenarios. Using some enumeration, find out the patterns, and you're just good to go. Let me help you do this. See? A0 is equal to 1, 2, 0, 0, 2, to 0, right? Just give me a second. 1, 2, 0, 2, 2. Yeah, 2. Yes. A1 is actually 1, 2, 0, 3, 0, 8 is actually equal to 10 times. Is that right? That actually is 10, A0 plus 228. Then A2 is actually A1203308. It's actually equal to 10 times 1, 2, 2, 8. 10 A1 plus 228. Is that right? You can actually do A3 and A4, but you already get a basic pattern. You see? There's always 10 times the previous term and then plus 228. 10 times the previous term plus 228. People might ask me, how come you can figure out that? It's not something too magic. I'm just going to show you something fairly quick. You see? What, like, oh, excuse me. Oops. Okay. The first term you have what? 12008, right? The second term is 12038. What are you going to do? You have to times 10, right? And then do a difference. The difference is 228, right? And then moving forward, 12038, 1203308. To make sure these are comparable, you have to basically times the 10 and then divide just by the last three terms. Not divide, subtract for the last three terms. Then you also have 228. Is that right? There's like not really like a mathematical pattern for this, but you kind of like figure out, as long as you keep adding a number, inserting a number in the middle, you're expanding your like entire number. So this number is actually just times 10 and add a certain number, so on and so forth. So that being said, AN is actually equal to 10 times AN 228, right? So, okay, here I want to give a quick comment. Trust me, these kind of problems, what we call is the bit manipulation problem. You have a number, you want to manipulate certain bits and then make the number longer or shorter. We call it the bit manipulation problem. The bit manipulation problem, normally, if you want to find a recurrence formula of different terms, you're always looking at something what I put in my screen. That's easy. In that case, we're going to do the mathematical induction method, right? Let's do this. Okay, so it always goes like this. Okay, so you have like the relationship between any two adjacent terms are always a multiplication and then put some number or subtract some number. So this is a common practice. Okay, you can see this problem very often. In today's homework, you're going to see you're actually going to see another similar problem as well. This is the bit manipulation problem. Okay. First, when n is equal to 1 or 0, whatever, because like the initial part is not always important, right? We have A0, 1, 2, 0, 0, 8. Of course, this is divisible by 19, right? Second, we suppose if n equals to k plus 1, if when n equals to k, the condition holds. That means ak can be divisible by 19. So let us check. N is equal to k plus 1. So ak plus 1 will be what? 10 times ak plus 228, right? 10 times ak, 228 is actually 819 times 12. Like I said, every number must be given for a reason. This is not a random number. So for sure, ak plus 1 can be divisible by 19 as well, right? So using the mathematical induction method, we're going to say, therefore, 19 is a divisor of an, for n belongs to all the positive integers. Is that right? If you don't quite understand the mathematical induction method per se, it's not a big problem because this is not covered. This is not a big topic for our current session. But the big methodology you guys need to understand. The big methodology is as long as you have such a pattern, you add 1, 3, add 2, 3, add 3, 3, whatever 3, you're going to actually create a sequence. So you're trying to prove that every single term in this sequence is actually divisible by using 19, right? So how to do such a kind of question? We always do mathematical induction. N equals to 0, it works. Suppose n equals to k, it works. Trying to prove it also works for n equals to k plus 1. The n equals to k plus 1, you need to actually use the hypothesis you did for n equals to k, which is actually here. The relationship is here, ak and ak plus 1. So this part, nothing tricky. You just do a little bit of observation, write out several terms, find out a pattern, and you're good to go. You guys follow me? Is it good? Like I said, if you're not familiar with mathematical induction, it doesn't matter. But you need to understand what I'm trying to say here. A question using human language to denote, you can never solve it out. You need to convert it into a mathematical language. The mathematical language is to basically construct a sequence. These are like the certain terms, certain items in the sequence. All right, I think that's pretty much for today's lecture. Yeah, I think that's pretty much. You have any questions for me? Oh, good. So like a quick recap, we actually introduced the basic concepts for the divisibility, right? We start with the definition and some basic properties. Divisibility is actually part you learn pretty much from your elementary school, so it's not a big problem whatsoever. So whenever you do the divisibility, there are like certain rules, certain tricks we have already introduced in our different problems, try to find out a pattern, right? You can see problems with like a sequence, you can see problems with a kind of like a counting probabilities. Always try to find a pattern using either the mathematical induction or either doing some language translation. So the $1 million part is how to understand the thought rather than like a regular solution for the problems. Okay, moving forward for the next lecture, we're going to go for the prime numbers and composite numbers, which is also a very important topic for the number theories. All right, you guys have any questions? So far, so good? Oh, good. All right, in that case, I'm going to publish the assignment in our Google Class. I think you guys would already have access. If you go to the Google Classroom, you can find our assignment as a PDF. So try to do the assignment. You can upload it after today's lecture, or we can just figure it out for the next lecture. All right, so any more questions? Oh, good. All right, thank you guys. And I'll see you guys for tomorrow's lecture. Bye, guys.